So hello friends and welcome back to your channel GATEquestionsECE, and this is the same question that I discussed in previous 3 videos. This is the fourth video on this question, and in this video I will be discussing the part B of this question using CDF method. I have already made 3 videos on this question in which I have discussed part A. In first video I have discussed part A using p.m.f method. In second video, I have discussed part A using CDF method, and in third video, I have discussed the part B using p.m.f method. So in this video, I will be discussing the part B, solution of part B using CDF method. For those students who haven't watched the part 1, 2 and 3 videos of this question, I request them to please go and watch those 3 videos. The link of those 3 videos is provided here in your I button. So I request you to go and watch those 3 videos for better understanding, because in these 3 videos I have done detailed analysis how to handle this maximum and minimum function using these two methods, p.m.f method and CDF method. So in this video I will be giving you the solution of minimum function using CDF method. So let's see how to solve using CDF method. So before going to the solution of part B of this problem, I will like to make you understand how the CDF of this function Z2 will look like. And to understand how the CDF will look like, we need to understand these 4 conclusions about this Z2 is equal to minimum x1 x2 function. So out of these 4 conclusions, first 2 conclusions I have already explained in the video 3 of this question. For those students who haven't watched video 3, I will explain these 2 parts once again. So let's see what is the first point. We will understand the first point with the help of an example. So let's see what are those possible values of x1 and x2 for which z2 is equal to 3. What are the possible values of x1 and x2 in this x1 x2 plane for which z2 is equal to 3? So if we take any point on this boundary with corner at 3, 3, you can see that on this boundary z2 will be equal to 3. For example, if I take a point here, so this point will be, so it will be 3, 6. Here it is 5, here it is 6. So this point is 3, 6. You can observe at this point that what will be the value of z2. Here z2 is minimum among x1, x2. Here x1 is 3 and x2 is 6. So minimum among 3 and 6 is 3. So z2 is 3 for this point. Similarly, for any other point lying on this section of this boundary, you can observe that z2 will come out to be 3. Similarly, at this point 3, 3, you can observe that z2 value will be 3. You can observe here both x1 and x2 are 3 here. So minimum 1, 3, 3 will be 3. So here at this point also z2 is 3. Similarly, on this side, on this section of the boundary, you can observe if we take any point on this boundary, for example, I take this point. This point will be 5, 3. So if I observe what will be the value of z2 at this point, so z2 will be minimum 1, 5, 3. So z2 will be 3. Similarly, you can observe for any other point on this section of the boundary, Z2 will be 3. So on this entire boundary here, which this boundary extends here up to infinity, this boundary extends here up to infinity, you can observe on this entire boundary Z2 is fixed and is equal to 3. So on this entire L-shaped boundary with corner at 3, 3, random variable capital Z2 will be equal to 3. You also note down that there is no other point in this entire x1 x2 plane where minimum among x1 x2 will be equal to 3. For example, you can take any other point here. For a test purpose, I am taking this point. So let's calculate what is the value of Z2 at this point. So this point is here x1 is -3 and x2 is 4. So this point is -3, 4. So minimum among this is -3. So Z2 is -3 at this point. So similarly, you can take all other points in x1 x2 plane, anywhere in x1 x2 plane, and you can observe that there are no other points in x1 x2 plane where Z2 is 3. So this boundary that I have drawn here is the points lying on this boundary are the only points in x1 x2 plane where Z2 is 3. So we can generalize this observation that any such L-shaped boundary with corner at 3, 3 will be boundary for Z2 is equal to 3. We can generalize this observation that any L-shaped boundary with corner at Z2, Z2 will be the boundary for capital Z2 is equal to small z2, where small z2 is the corner point of this L-shaped boundary. So this is the first conclusion. Now I will read it. In x1 x2 plane, in this x1 x2 plane, the capital Z2 is equal to small z2 is the L-shaped boundary with corner at small z2, small z2. So capital Z2 is equal to small z2. This corresponds to this L-shaped boundary in this x1 x2 plane whose corner is at small z2, small z2. And on this L-shaped boundary, capital Z2 is fixed and its value is small z2. So this is some fixed value. So now we will understand what is conclusion 2. So the conclusion 2 states that probability capital Z2 is equal to small z2 will be equal to sum of joint probabilities of all ordered pairs or all points which are lying in x1 x2 plane on this L-shaped boundary. So if you want to calculate this probability, it will be nothing but the sum of joint probability of all the points that are lying in this on this boundary. If there are no points in joint distribution of x1 x2 that are lying on this boundary, then this probability will be 0. It will be non-zero only if the joint distribution of x1 and x2 have points lying on this boundary. Only then the probability capital Z2 is equal to small z2 will be non-zero and will be equal to the sum of joint probabilities of ordered pairs lying on L-shaped boundary with corner Z2, Z2. So this probability will be equal to sum of all the joint probabilities of possible ordered pairs in the distribution of x1 and x2. So hopefully you have understood these 2 points. So now we will see what is the third conclusion. To understand third conclusion, we will again take example of Z2 is equal to 3. Since we know that Z2 is equal to 3 is this boundary in x1 x2 plane. On this boundary Z2 is 3. So let's see what are the possible boundaries for case Z2 greater than 3. For example, Z2 is 4. So let's see where does this boundary lies in this x1 x2 plane. So this boundary Z2 is equal to 4 will lie in this x1 x2 plane with corner at 4 comma 4. So here this corner will lie here and corresponding will be the boundary that I am going to draw now. So this L-shaped boundary is the boundary for Z2 is equal to 4. Similarly, for all the values which are greater than 3, for example 3.1, 3.2, 3.3, 3.4, all the real values which are greater than 3, we can draw the boundaries here in the right side of this Z2 is equal to 3 line. So for Z2 greater than 3, we can see all the boundaries for which Z2 is greater than 3 will lie to the right of this Z2 is equal to 3 line. So this whole region which lies to the right of this Z2 is equal to 3 line, we can say that region is Z2 is greater than 3. And similarly, to the left of this boundary, Z2 is equal to 3 boundary, to the left of this boundary we can see we can draw different L-shaped boundaries for which Z2 will be less than 3. So similarly, in general, if this is Z2 is equal to small z2 boundary, then to the right of this boundary, all the boundaries will have Z2, capital Z2 is greater than small z2. So in this yellow region, we will have all the boundaries. In this yellow region, we will have all the boundaries which will satisfy this condition. So the collection of all those L-shaped boundaries which lie to the left of this capital Z2 is equal to small z2 line will always satisfy Z2 is less than Z2. So all those L-shaped boundaries which we can draw to the left of this L-shaped boundary, the collection of all those L-shaped boundary will satisfy capital Z2 is less than small z. So hence we can conclude that in third point that capital Z2 is greater than Z2 is the region lying to the right of boundary capital Z2 is small z2. So in this xy plane, on this line capital Z2 is small z2, and the region that is lying to the right of this line is the region where capital Z2 is greater than small z2, and the region that is lying to the left of this line capital Z2 is equal to small z2, the region that is lying to left of this line or boundary is the region that satisfies capital Z2 is less than small z2. So this is the fourth conclusion. So now we will use all this information to define the CDF of Z2. Since we know that the CDF of Z2 is represented by this expression, so this is equal to probability that capital Z2 is less than equal to small z2. So you observe this inequality. You see, you can look here in this x1 x2 plane and observe that capital Z2 is less than equal to Z2. Small z2 is the region which includes this whole green region as well as this boundary. So this CDF of Z2 is nothing but the sum of all the joint probabilities that lie in this green region as well as on this red boundary of capital Z2 is equal to small z2. So it is sum of all joint probabilities lying in region Z2 less than Z2 and boundary Z2 is equal to small z2. So this probability is the sum of all the joint probabilities that are lying in this green region of capital Z2 is less than small z2, and on this boundary capital Z2 is equal to small z2. So this is the graphical definition of CDF of Z2, which is minimum among x1 and x2. So now we will use this graphical definition of Z2 in finding the solution to our problem B of question number 102. So let's see its solution now. So it's given in problem that x1 is uniformly distributed over -1 to 1. So x1 can take three values, -1, 0 and 1, and the probability that x1 is equal to some sample value small x1 will be 1 by 3 in each of these cases. Similarly, it's given that x2 is uniformly distributed over -2 to 2. So x2 can take 5 values from -2, -1, 0, 1 and 2, and the probability, here it is x2. Probability x2, capital X2 is equal to sample value small x2 will be 1 by 5 for all of these 5 cases. So the joint probability of x2 and x1 will be the product of marginal probabilities of x1 and x2. Why? Because here x1 and x2 are independent events. So we can see in each case, in all these three cases, it's 1 by 3 here. So it's 1 by 3, and all these 5 cases it's 1 by 5. So the answer will be 1 by 15. So its joint probability will be 1 by 15 for all the ordered pairs which are formed by the Cartesian product of this set and this set. So for when x1 is -1, x2 can take 5 values. So these 5 values correspond to these 5 red dots in this x1, x2 plane. When x1 is 0, x2 can again take these 5 values. So these 5 ordered pairs correspond to this case. So when x1 is 1 and x2 can take these 5 values, so we can get these 5 ordered pairs in this case. So the joint probability for all these 15 ordered pairs will be 1 by 15. Now let's see what will be the CDF of Z2. So Z2 is minimum x1, x2. So the CDF of Z2, which will be represented by f Z2 sample value small z2 will be equal to probability that Z2 is less than equal to small z2 and will be equal to. So now we will calculate the CDF of Z2. Firstly, you can notice in this diagram that the leftmost boundary here will have corner at -infinity, -infinity on x1 is equal to x2 line, and corresponding value of z2 on this L-shaped boundary will be -infinity. Similarly, the rightmost boundary here will have corner at +infinity, infinity, and for that L-shaped boundary z2 will be +infinity. And in between we can see as we move from -infinity, -infinity to increasing points up to +infinity, +infinity, we can note that Z2 is increasing from minus infinity to plus infinity. So as we move from left to the right on x1 is equal to x2 line, we can see there is increase in Z2 values. According to the definition of CDF of Z2, there is no point out of these 15 points, there is no point that is lying to the left of this leftmost boundary or on this boundary. So for Z2 is equal to minus infinity, we can see this probability will be 0. If we move this boundary until we reach at this point, we can still see that there are no points out of these 15 points that are lying to the left of this boundary or on this boundary. So still for this value of Z2, we can still say that this CDF value will be 0. If we still move this boundary up to this point where Z2 is minus 2, this boundary is Z2 is minus 2 boundary, until we reach at this point, there we can see there can never be any point of this out of these 15 points that will lie to the left or on this boundary until we reach this particular boundary, this blue boundary where Z2 is minus 2 on this boundary. So first conclusion we can write, for Z2 less than minus 2, we can say that there is no point out of these 15 points for any boundary that is lying in this region. Z2 is less than minus 2. So in this whole region, there is no such boundary for which there is overlapping with these 15 points. So this probability is 0. So next we consider the case of boundaries Z2 is greater than equal to minus 2 and less than 1. If you consider all the boundaries that are lying in this region, so I am talking about this blue boundary as well as the boundaries that are lying to the right of this blue line and to the left of this yellow line. So in between this region, this whole region is the region that is given by this inequality. So for all such cases, you can see here, if I draw a boundary here, you can see there are only these three ordered pairs which are lying to the left of this boundary. So for this case, the CDF will be the sum of these three joint probabilities. So the answer will be 3/15 for this case. So next we can talk about the region that includes this minus 1 region. So this will be minus 1. This minus 1 boundary as well as to the right of this minus 1 boundary, but to the left of this Z2 is equal to 0 boundary. So in between this, so we can see by drawing here such boundary that in such case there are these 5 points and these 4 points which are lying to the left or either on this line. So in this case there are 9 points which are lying to the left of this boundary. So the answer will be 9/15. Sum of all joint probabilities of all these 9 points will be 9/15. So similarly, we can consider the case of boundaries which lie in this region. We can see that the boundaries that are lying in this region are the boundaries which include this Z2 is equal to 0 boundary as well as boundaries that are lying to the right of this Z2 is equal to 0 line, but to the left of this Z2 is equal to 1 line. So for any such boundary we can draw here. So we can see there are these points that are lying to the left of this boundary. So sum of the joint probabilities of these points, so these are 13 points. Sum of the joint probability of these 13 points is 13/15. So next we consider the case of boundaries which lie in this region. So Z2 is greater than equal to 1 is the region which includes this Z2 is equal to 1 boundary and all boundaries that lie to the right of this boundary. So in this case, we can consider any such case here. So for all such boundaries, we can see it includes all these 15 points to the left of this boundary, 15 by 15, which is nothing but 1. So this is the CDF of Z2. We can plot this CDF of Z2, which I am going to do on the next page. So this was the CDF expression that we derived on the previous page. I have copied it here. So let's draw the CDF of Z2. On this axis, I will be writing the value of CDF, and this axis is Z2 axis. So the first expression here says for all the values of Z2 less than -2. So this is -2. So below it, so below the values of -2, we can see here that value of Z2 is 0 here. And for the value of Z2 between -2 to -1, its value is 3 by 5. So we can see here that between -2 to -1, its value is 3 by 15. Similarly, in this range from -1 to 0, its value is 9 by 15. So here -1 to 0, we can see its value is 9 by 15. Similarly, we can draw for these two ranges also. So we can see this is the final CDF diagram of Z2, where Z2 is minimum of x1, x2. So now we can easily calculate the p.m.f of Z2 from this CDF diagram. How can we calculate? We know that the CDF of a discrete random variable will be a step size diagram. So here we can see there are steps in this diagram. We also know that the non-zero probability of a discrete random variable is equal to the value of the step in the CDF of discrete random variable. So here we can see when Z2 is -2, there is a step change. So first non-zero probability will be when Z2 is -2, and the corresponding probability will be, its probability will be 3 by 15 minus 0. So its probability is equal to the step change occurring at -2. Similarly, we can see when Z2 is -1, there is a step change here. So the probability for -1 when Z2 is -1 is equal to 9 by 15 minus 3 by 15. So it's 6 by 15. Similarly, when Z2 is 0, we can see here is a step change. So the size of step change is 13 by 15 minus 9 by 15, which is 4 by 15. So its probability is 4 by 15. Similarly, at 1, we can see there is a step change. So the size of step change here is 15 by 15 minus 13 by 15. So it's at point at Z2 is 1. So its probability is 2 by 15. After that, there is no step change. So for all other values of Z2, the probabilities will be 0. So this is the p.m.f of Z2. So this is how you can calculate the p.m.f of Z2 using CDF method.